हेलो चिल्ड्रन, आज इस लेक्चर में हम लोग स्टार्ट करेंगे केमिकल प्रॉपर्टीज़ ऑफ एल्काइल हैलाइड्स. ओके, सो केमिकल प्रॉपर्टीज़ ऑफ एल्काइल हैलाइड्स. फर्स्ट वी विल डिस्कस reactivity of haloalkanes. Reactivity of haloalkanes. Okay children, so for reactivity of haloalkanes, the reactivity of haloalkanes decreases in the order from alkyl iodide to alkyl fluoride. Okay children, so alkyl fluorides are least reactive, whereas alkyl iodide are most reactive due to the increase in bond dissociation energy in this order. Okay children, so from alkyl iodide to alkyl fluoride, bond dissociation energy of CX bond increases, and that is why a reactivity of related alkyl halides decreases. So the bond dissociation energy of alkyl iodide is least, and that is why these are most reactive, whereas this dissociation energy of alkyl fluoride is highest, and that is why these are least reactive. Okay children, so first we will discuss nucleophilic substitution reaction. Nucleophilic substitution reaction. Nucleophilic substitution. Okay children, so nucleophilic substitution reactions are the reactions in which attacking reagent is a nucleophile. Okay children, for example, if this is a hypothetical base compound and a nucleophile Y is going to attack here to form the compound A Y plus B minus. So nucleophilic substitution reactions are the reactions in which attacking reagent is a nucleophile. Okay children, and it is a type of substitution, and also you can see here that leaving or forming byproduct is also a nucleophile. Okay children, so comparatively strong nucleophile displaces comparatively weak nucleophile from the base compound. So such type of reactions are known as nucleophilic substitution reactions. Okay children, so in alkyl halides, the halogen atom also displaced by stronger nucleophiles like hydroxide, cyanide, and amino group. Okay children, so these are the comparatively stronger nucleophiles which displace halogen atom from alkyl halides to form a different type of compounds. Okay children, so nucleophilic substitution reaction. Nucleophilic substitution reaction, in short we can represent nucleophilic substitution reactions as NS, nucleophilic substitution, and these are of two types: nucleophilic substitution first order and nucleophilic substitution second order reaction. Okay children, nucleophilic substitution first order reaction and nucleophilic substitution second order reaction. So nucleophilic substitution first order reaction, we will discuss this type of substitution first. Okay, so nucleophilic substitution first order. Okay children, first order reaction. So this substitution is a type of first order reaction. Why? Because only one reactant compound is responsible for the rate of reaction, or you can say that change in concentration of one reactant only is direct to the rate of reaction, or you can say that only the concentration change of one reactant is govern the rate of the reaction. Okay children, so such type of changes are known as first order reaction. So SN1 mechanism or SN1 substitutions are of two-step change. Okay children, so in first step formation of carbonium ion is taking place. Formation of carbonium ion. So alkyl halide we can represent in this way. Okay, and you know that this relation is a polar relation. So this is partially a negative center, this is partially positive center, and this is partially a negative center. Okay, because halogen is more electronegative than carbon. So this is a alkyl halide, and in first step this alkyl halide converted in the form of carbonium ion. Okay children, so carbonium ion, the ion in which central carbon atom is positively charged, carbonium ion, and plus halide ion is formed. Okay, so this is the first step, and the first step is formation of carbonium ion. Okay children, so this conversion from alkyl halide to carbonium ion formation is a slow step, and we know that if any chemical change is taking place more than one different steps, then the slowest step is known as rate determining step. So for this SN1 change, the first step in which formation of carbonium ion is taking place will be a slower step, and that is why this is rate determining step also. And in this step only one reactant molecule is present, so the rate of whole conversion will be depend upon the concentration change of this alkyl halide molecule only. Okay children, so due to the only one reactant molecule is determining the rate of reaction, that is why this change is known as first order reaction. Okay children, so in first step carbonium ion is formed, and the second step attack of nucleophile and formation of product. So in second step, on this positive side of the carbonium ion, incoming nucleophile will attack, and due to this attack formation of final product will take place. So this is carbonium ion which is formed in first step, and this will be attacked by nucleophile, let hydroxide ion. So this will attack this site, and due to this attack finally product will form, which will be alcohol in this case. Okay children, so this is the SN1 mechanism of substitution reaction. So SN1 mechanism is two-step mechanism. In first step carbonium ion is formed, and in second step this carbonium ion is get attacked by nucleophile, incoming nucleophile, and finally the product is formed. Okay children, SN1 reaction. So in SN1 mechanism, this carbonium ion is formed as intermediate, and you know that carbonium ion is having trigonal planar structure. Okay, and due to this planar structure of this carbonium ion, which is formed here as an intermediate, this incoming nucleophile can be attacked on this site of the carbonium ion from this side or this side. With equal efficiency. Okay, so due to the planar structure, this carbonium ion can be attacked by this nucleophile from, you can say, back side and from front side equally. Okay, so due to this, 50% attack of this from this side and 50% attack of from this side will takes place here on this positive carbon side. And due to this two type of attack, two different products are formed which are having difference in the configuration of the valency. Okay children, so due to this attack, you can say this attack as back attack or this as front attack. So due to this back attack, when this nucleophile will approach towards this carbon site, these three valencies will be concentrated to the opposite side of the attack of nucleophile. Okay, because it is a comparatively polar or electron rich unit, so it will repel these all three valencies, and these valencies will get concentrated opposite side of the attack of this nucleophile. Okay, so the configuration of the valencies will be in this way. Okay, due to this back attack, and due to this front attack, the configuration will be opposite in this way. Okay children, so overall two different configuration product will form finally. Okay, and these two are optically active in nature, and as you can see here in these two structures, these are enantiomers, optically active and enantiomers. So this can rotate monopolar light towards this side, and this can rotate monopolar light towards this side. Okay, so due to the 50% attack, these two enantiomers will be formed in 50% amount. Okay, so overall 50% amount of these two products will form in the form of a mixture under SN1 mechanism, and this mixture will be known as racemic mixture. Okay children, so overall in SN1 mechanism, which is taking place in two steps, finally a racemic mixture is formed of two enantiomers. Okay, so racemic mixture is a mixture in which two enantiomers are present of a particular compound. Okay, so the product form which is having configuration opposite to the base compound. Where is the base compound? This one. So as you can see, the configuration of the three valencies are of this side, are here in this product, is opposite side of the base compound. So the product molecule which is having opposite configuration of the base will be known as inverted form. And the formation of inverted form is known as inversion. Formation reaction is known as inversion, and whereas the product which is having same configuration as present in base compound, so the formation of this similar configuration product is known as retention, and the form which is formed here is known as retained form. Okay children, so 50% of both the forms will form here, 50% inverted form, 50% retained form, and that is why overall this mixture will be formed, which is known as racemic mixture, and formation of racemic mixture is known as racemization. Formation reaction of racemic mixture is known as racemization. Okay children, the next type of nucleophilic substitution is SN2 mechanism, SN2 reaction. So it is a second order reaction. Okay children, it means its rate, the rate of SN2 reaction is depend upon both the base compound and also on the reagent. Okay, that is why this mechanism is second order change or second order mechanism. Okay, so for example, it is a base compound, okay, and nucleophile OH. Okay children, so when this nucleophile attacks here on this base compound, an intermediate state is formed, which is known as transition state. Okay, so this transition state is formed in which central carbon atom is pentavalent. Okay, this transition state is formed. So this central carbon atom is pentavalent in position, and this bond is in the state of formation between hydroxide group and carbon, and this bond is in the state of breaking, which is present here between halogen and carbon. Okay, so simultaneously two conditions are here. This bond is forming and this bond is breaking. So this we show in the form of this type of dashed lines. Okay, so at this state, which is known as transition state, central carbon atom is showing itself as a pentavalent center. Okay, and it is a very high energetic state, and that is why unstable, and very quickly this state converted in the form of product and nucleophile. Okay, so product is formed plus nucleophile. So this SN2 mechanism, which is second order reaction, is overall taking place in one step, and in this step the nucleophile is attacking from the back side. Why? Because in front side this nucleophile is present, so it will not allow this nucleophile to attack on this side from this side, because this nucleophile is present here. Okay, so this nucleophile itself electron rich unit, and when this nucleophile will try to attack from this side, this nucleophile will repel to this incoming nucleophile. Okay, so to avoid this hindrance, this nucleophile will attack from back side, from this side. Okay, so this side it will attack to this center carbon atom, and after attack this intermediate state is formed, which is known as transition state, very high energetic state, and that is why unstable, and it will break in the form of product plus nucleophile. So as you can see here, both the base compound and nucleophile is taking place in this reaction. That is why this reaction is a second order reaction or second order mechanism. Okay children, then second thing which is very important, that the product which is finally formed here in SN2 mechanism is having opposite configuration of the base compound. Okay, so about 100% inversion in taking place in SN2 reaction, and the product which is formed is having opposite configuration than the starting base compound. Okay, so in SN1 reaction both retention and inversion is taking place 50-50%, but here only inversion is taking place, retention is not here. Okay, so no racemic mixture will form in the SN2 mechanism. Then after this, number of small points are here, and those points we will discuss with the help of your book only. Okay children, so the order of reactivity of SN2 reaction is primary halide to secondary and tertiary. So this is the order of reactivity of halides in SN2 mechanism. Okay children, so primary halides will be most reactive and tertiary halides will be least reactive for SN2 mechanism, whereas for SN1 mechanism the reactivity order will be opposite of this, means tertiary halides will be most reactive for SN1 mechanism and primary halide will be least reactive. Okay children, then next heading is stereochemical aspects of nucleophilic substitution reactions, and the first heading is plain polarized light. So these all term you was having in your 11th class also, but here we can revise it, these all the points or terms once again in a very short manner. So first heading is plain polarized light. Okay, so the light which is having one color only is known as plain polarized light. Okay, or you can say that when a normal light is passed through a nickel prism, so all different parts of the light, color of the lights get absorbed except one. Okay, so the light which is obtained through the nickel prism, which is having just one color light beam, is known as monochromatic light or plain polarized light. Okay children, so monochromatic light is also known as plain polarized light, and plain polarized light is having oscillation in only one direction, Okay children, oscillation in only one direction. So for the study of optical activity we are required plain polarized light. The next term is optical activity. Okay, so the compounds which show sensitivity for monopolar light or monochromatic light are known as optically active compound. Okay, and their sensitivity is known as optical activity. Under this sensitivity they rotate monopolar light in two different directions. So when the light is rotated towards the right hand side, compounds are known as dextrorotatory, and when it rotated towards left hand side, the related compound is known as levorotatory. Okay, so this rotation amount we can measure with the help of an instrument which is known as polarimeter. The next heading is cause of optical activity. So cause of optical activity, for the organic compounds, the related compound should have asymmetric carbon atom, or stereocenter. Okay, so such compounds which are having asymmetric carbon atom or stereocenter will be optically active. Now, what is the meaning of asymmetric carbon atom or stereocenter? So the carbon atom in which its all four valencies get satisfied by different groups or atoms, such carbon atoms are known as asymmetric carbon atom or stereocenter. And also one term is used, that is chiral carbon atom. Chiral, CHIRAL, chiral carbon atom, and the molecules which are having chiral carbon atom are known as chiral molecules. Okay, few examples are given here of different compounds. So in the first compound, this is the chiral center or asymmetric center. With this carbon, 4 different groups are attached. Here also 4 different groups. Here also 4 different groups are attached. Okay, so such compounds will be optically active compound. Then there are some compounds which are having chiral carbon but are not optically active. Okay, children. So in short, we can say that optical activity is not based only on asymmetric carbon atom or stereocenter. Okay, so the compound which are having no any type of plane of symmetry will be optically active compound. No any type of plane of symmetry. Okay, such compounds will be optically active, and also the molecules does not superimpose on its mirror image. Okay, so such compounds will also optically active. Children, optical isomers are of two types. Enantiomers are the optical isomers which are mirror image of each other, and diastereomers isomers, these are the optical isomers which are not mirror images of each other. Okay, children, so we can divide optical isomers under 3 categories. D or L form means dextrorotatory, L or minus form means levorotatory. So dextro and levo will be enantiomers. Okay, and the next is meso form. So these are the optical isomers which are optically inactive, non-chiral and is symmetrical. It can be divided into 2 identical halves. Okay, children, so these are optically inactive, known as meso form. Next heading, optical isomerism in lactic acid. So lactic acid is showing 2 enantiomers, these 2 forms which are mirror images of each other, D-lactic acid and L-lactic acid. Okay, children, dextrorotatory and levorotatory. Then optical isomerism in tartaric acid. Tartaric acid is showing 3 optical isomeric forms: dextro, levo and meso. Okay children, so as you can see here, the first one is dextro form, the second one is levo form, dextro rotatory, D form, levo rotatory, and the last one is meso tartaric acid or meso form, which is optically inactive. So as you can see here in this structure, due to the presence of this line of symmetry, this compound is optically inactive, whereas it is having 2 asymmetric carbon atoms in it. Okay, but due to the presence of this line of symmetry, this is optically inactive. Okay, so this is the diastereomers. This is the diastereomer. Okay, because it is not having any relation of mirror images with these 2 isomers. Okay, the next is two terms are there: external compensation, and same way there are 2 types of compensation: external and internal. External and internal. Okay children, so if any racemic mixture, equal amount of 2 different enantiomers of same compound is present, then that mixture will be optically inactive. Okay, and this phenomenon is known as external compensation. Okay, external compensation. So formation of a racemic mixture by mixing equal amount of 2 different forms of 2 different optically active compound of same compound. So that this is known as external compensation. And if in a compound such 2 same part of the structure are present, due to which the compound itself is a non-optically active or non-optically active, so such compensation is known as internal compensation. Okay, so in meso form of tartaric acid, internal compensation is present. Internal compensation is present. Okay children, so it is optically inactive due to internal compensation, and when we mix equal amount of these 2, so the mixture will be optically inactive due to external compensation. Okay children,